Welcome back to recitation. Today we're going to work on a problem involving differential equations. I'm going to read it to you, give you a little hint, give you some time to work on it, and then I'll be back and work it out for you. So the problem is to find a function y equals f of x that has the following two properties. D squared y dx squared is equal to 6x, and just to remind you what this means, this is the second derivative of y with respect to x. Okay, so its second derivative with respect to x should be 6x. And the second condition is kind of long, but it says the graph of the function in the xy plane passes through the point 1, 1 with a horizontal tangent there. So let me give you one hint, and that hint is that there are some initial conditions buried in here. That's why we have this condition. So I'm going to give you a little bit of time to work on it, and I'll be back and I'll work it out with you. Welcome back. Hopefully you were able to start at least solving the problem initially, give yourself a little direction. So let's see how you did. Okay, so the first thing I would like to do is try and figure out maybe what the first derivative of the function y equals f of x is. I have its second derivative, so in order to find the first derivative, I want to find ultimately a function that when I take its derivative, I get 6x, right? So we can think about this. Maybe the easiest thing for us to do would actually be to consider another function whose derivative is 6x, and we'll know that's dy dx. So I'm going to say this d squared y dx squared, I'm going to say is the first derivative of another function. We'll say dw dx. And the reason I'm going to do that is so we're not too nervous about how we solve this problem. So let's just assume that. So I'm introducing another function w, which is the first derivative of y with respect to x ultimately, because its derivative is the second derivative of y with respect to x. So let's see how to solve the differential equation dw dx equals 6x. Now, you may be able to do that right away. You may see what this is right away. If you're a little nervous, we can do a separation of variables. So right away, maybe some of you can see that this will be 3x squared. But let's just double check. So separation of variables, on this side we get the integral of dw. On this side we get the integral of 6x dx. Here we get a w. And here, again, we should really do 6x squared over 2 plus a constant. So that's 3x squared plus a constant. I'm going to write C1 here because we're going to need a little bit of information. We're going to need another constant later. So we actually now know the derivative of y with respect to x. What we found here, I'll just write that in, is dy dx. Again, let me remind you why. We were saying the second derivative of y with respect to x we're going to call dw dx. So when I took an integral of dw dx, I got w. So that means I've taken one antiderivative here, and so now I have dy dx. So this is dy dx. I'm going to draw a line, and now we want to find y. And again, we can use separation of variables, or this time I'm just going to do the problem without separating variables because I actually know what an antiderivative is of this, what an antiderivative is of this, and then I need to add one more constant. So I can say that y is definitely equal to x cubed plus c1x plus c2. And let me just, again, let's see why that is. Right, this antiderivative of this is x cubed. Antiderivative of this it's a constant, so its antiderivative is a c1 times x. And then I have to add on another constant because I have a whole family of possible solutions. So here I have y, and now I need to figure out how to use number 2. Maybe before you even go on, you want to check, does this really satisfy number 1? So if we wanted to check that, we just take two derivatives of this expression on the right-hand side. Two derivatives of this is 0. Two derivatives of this is 0. And two derivatives of this is 6x. So I do indeed get what I want. So now we definitely can go on to number 2. OK? So what do we have? Number 2, it says we have some initial conditions here. The graph in the xy plane passes through the point 1, 1, and it has a horizontal tangent there. Now, what does that actually mean? Let's think about that. That actually means that 2 says f of 1 equals 1, right? Y is equal to f of x. So we can write this also as f of x. So 2, the first part says f of 1 is 1. And what does this second condition? Let's check the second condition. It says it has a horizontal tangent there. Horizontal tangent means that its derivative at that x value is 0. So let me write down that in a nice form. The derivative at that x value is equal to 0. This is a little different maybe from what we've seen previously. In the lecture, you saw examples, at least certainly where you had one initial condition. Here we need 2 initial conditions. And you see why is because we actually have 2 constants. Where did that come from? It's because we started with a second derivative instead of just a first derivative. So that's why you see more initial conditions than maybe you've seen previously. So let's plug these in and let's see what we get. If f of 1 equals 1, then let's evaluate that. F of 1 is equal to 1 cubed plus 1 times c1 plus 1 time, or just 1 there, or c2 there, sorry. There's no x there, so just c2. And that all has to equal 1. Right? And then let's look at what the derivative is. The derivative is still over here. So f prime at 1 is equal to 3 times 1 squared, so 3 times 1, plus c1. And the condition says that equals 0. Equals 0. So we can read off, the nice thing is this is a system of equations, but one of them is very easy to solve initially, then we can substitute. So what does this say? Well, 3 plus c1 equals 0, so c1 is equal to minus 3, negative 3. If I plug in negative 3 for c1 in this expression, in this equation up here, I get negative 3 plus 1 plus c2 has to equal 1. If I subtract the 1s from both sides, I get negative 3 plus c2 has to equal 0. So c2 has to actually equal 3. So the final answer is evaluating or plugging in the c1 and the c2 in for the constants there. The final answer is x cubed minus 3x plus 3. So we started with a differential equation and 2 sets of initial conditions, and we came up with one solution that satisfies that. Now you can look at this, you could graph this on a calculator or a computer, and look and see if it satisfies that it's actually passes through the point 1, 1 and has a horizontal tangent there. But we know, based on our work, that that actually should happen. So I think that's where I'll stop.